Y is being added to whatever X is in the flask. So an example of that might be NaOH is titrated with HCl. That means NaOH is in the flask, and Y, the HCl, would be in the burette. So first of all, let's look at a titration curve here, where we're going to draw a titration curve of HCl with NaOH. So what that means is that the HCl in this case will be in the flask, and the NaOH will be in the burette. So let's look at an example of that, sort of step by step as we go through the titration. So a titration curve is always going to be pH on the y-axis, and then the volume of whatever happens to be in the burette will be on the x-axis. So if we start off and we've got just HCl in the flask, then the pH is going to be around about 1 because HCl is a strong acid. If we add 1 mole of OH minus, what's going to happen is that 1 mole of H plus will react with that 1 mole of OH minus immediately and turn into 1 mole of water. What I haven't shown in this flask is the water, but all of these solutions are aqueous. So the 1 OH minus we add is immediately destroyed and turned into water. What that leaves is 3 H pluses in the solution. As such, the pH will go up slightly because now it is less acidic. There's less acid in the solution, so the pH goes up a little bit. In this instance, we add another molecule of OH minus, so another H plus gets destroyed. It gets turned into water, and we're left with 2 H pluses, so now the pH goes up just a little bit more. We add another OH minus. We're left with 1 H plus in the solution, the other H plus turned into water. And again, the pH goes up a little bit more. Now at this point, we're going to add 1 more OH minus, and that's going to destroy the remaining H plus. And all we're left with in the flask right now is water. So the pH takes an immediate jump up to 7. It's important to note that this jump is a very sudden jump, because even here, when there's just a little bit of H plus in the solution, that's enough to keep the pH. Very low. But as soon as we destroy any trace of H plus by adding this OH minus, the pH immediately jumps to 7, and that's what we're seeing with the equivalence point. Then we add 1 more OH minus, and that's enough to jump the pH up to 12. That makes the pH very high because now we have a strong base, only a strong base in the solution. Alright, so you can see our general shape of our titration curve. We have the pH on the y-axis, we have the volume of NaOH on the x-axis. The reaction that's occurring, and this is what will show you what's happening at the equivalence point, is we've got 1 mole of HCl and 1 mole of NaOH. What that gives us is 1 mole of H2O, which comes from the H joining with the OH, and 1 mole of NaCl, which comes from the Na joining with the Cl. So at the equivalence point, this is what we would have. We'd have H2O and NaCl in the solution. The NaCl is completely neutral, so the pH at the equivalence point, which is here, is going to be neutral as well. If we reverse the situation, we now do a titration of NaOH with HCl. That means the NaOH will be in the flask, the HCl will be in the burette. So at the very beginning of the reaction, we're just going to have sodium hydroxide in the flask, and the initial pH will be 14. We'll keep on adding acid, that will drop the pH slightly as the solution becomes less basic. Once we get to here, the equivalence point, we've added as much NaOH, we've added as much HCl as we have NaOH in the solution, and the pH will drop to 7. Then we keep on adding acid, and the pH will drop to a very low pH because now we're just going to have acid in the containers. So it's just a reverse situation of what we had before. Still present at the equivalence point right here, just the HCl and the NaOH have joined to give H2O and NaCl. That's why the pH at the equivalence point is still 7. Notice it's pretty much just a mirror image of the previous one. Alright, let's look at what happens if we start off with the strong base and we use a weak acid as the thing we're going to titrate with. What's going to happen here is that we're going to start out with a pH of NaO of 14 for the sodium hydroxide. So that's where we're at here. And then we're going to add in acetic acid. Now as we add in the acetic acid, we need to realize that the final pH or the ending pH is going to be about 5 because that's the pH of a weak acid solution of acetic acid. We're not talking about HCl anymore, which is going to have a pH of 1 at the end. This is going to have a pH of about 5 at the end. Now the other thing that we need to consider is, since we're using a weak acid, is that when at the equivalence point, if we've got acetic acid here and we add sodium hydroxide, this is what's going to be present at the equivalence point. The H from here will react with the OH, that gives water, and what's left is the Na reacting with this, which gives this salt here. This is sodium acetate, and this sodium acetate salt is actually weakly basic, and it will have a pH of about 9. Now a good way to be able to tell what the equivalence point is going to be is to look at the starting pH, look at the ending pH, add them together and divide them by 2. So 14 plus 5 is 19, divided by 2 is about 9. That gives you an idea of where the pH of the equivalence point is going to be. So this is going to be a strong base that has been titrated with now a weak acid. Remember, weak acids don't have quite as low pHs as strong acids do. Of course, we can reverse this situation now, and we can titrate the acetic acid with sodium hydroxide. I want to talk about buffer regions in a separate mini lecture, so hold off on how we're going to tell when a buffer region occurs and where it's going to occur. So the same situation occurs here as occurred before, except now it's in reverse. We're going to start out with a pH of about 5 because that's all that's in the flask is this weak acid, acetic acid. We add the sodium hydroxide, we get a very slow increase in pH. In fact, we get a bit of a plateau here due to the buffering, which again I'll talk about later. And then we get to the equivalence point when the sodium hydroxide has eaten up all of the acetic acid that's in the solution, and we end up getting H2O and again sodium acetate, which is a basic salt and has a pH of about 9. So this is what's present at the equivalence point, just these two here. So again, we can figure out where the equivalence point is by getting pretty much the average of where we're starting, where we're finishing. We started out at the weak acid pH 5. We finished at the strong base of pH 14. We can also do stuff with strong acids and weak bases, and an example of that would be draw a titration curve of HCl with NH3. Now NH3 is ammonia and is also written as NH4OH, which is basically an ammonia solution in water. So it's NH3 plus H2O gives NH4OH. And you can really express it either way. Now if we start out with the HCl in the flask, then we're going to start out with a pH of 1. We're going to add ammonia, and the pH is going to go up slowly as the solution becomes less acidic. Then we're going to finish adding the HCl to the NH3, the NH3 to the HCl, because the NH3 will have eaten up all the HCl at this point. And at the equivalence point, what we've got is HCl plus NH3 gives NH4Cl. So this is the only thing present at the equivalence point. The other way we can write this is to use NH4OH, which is a little bit easier to see because you can see the H reacting with the OH to give water, but the NH4 still reacts with the Cl to give NH4Cl. So at the equivalence point, all we've got is NH4Cl, which happens to be slightly acidic. That's a weak base, NH4Cl. Now again, we can figure out what the pH at the equivalence point is going to be by looking at the average of the starting pH and the ending pH. Since NH3 is a weak base, the ending pH will be 9. The starting pH of the HCl will be 1. So the ending pH will be 5, which matches the fact that we've got only this weak acid NH4Cl present at the equivalence point. We can also do a titration of a weak base with a strong acid. So we start out with NH3, which is going to be a weak base, pH of 9 initially. We get this buffer region, this plateau again in this case, and then we keep on adding the HCl and the pH will drop. And after the HCl has eaten up all the NH3 that's in the solution, we're just left with NH4Cl at the equivalence point. Again, the pH will be 5 at the equivalence point, and you can still work out the equivalence point by getting the average of the beginning and ending pHs in the titration. The final pH will be 1 because all will be left within the solution is just that HCl being added, and it will override anything that's going on here with the NH4Cl and drop the pH right down here. If you start off with a weak acid and you titrate it with a weak base or vice versa, it's difficult to know what's going to happen there because the combinations of the salts are difficult to predict as to whether or not we're going to have an acidic or basic solution at the equivalence point. So it's hard to predict that.